Да есть у меня контакты и Вася, и Федя. Так, что-то я не понимаю. Паула, все, загорелась. Так, кто-нибудь, проверьте, пожалуйста, работает ли запись. Может так случиться, что ничего не будет работать. Работает, и звук есть. Okay, well, let's begin. So our goal for today and for the optimistic plan. First, last week I mentioned two theorems, and our step number 1. We identify the action of pi 1 of a on pi n of x comma a with the action of pi 1 of f on pi n of e comma f, which is basically follows from the fact that the diagram homotopy commutes. And now we need to understand the action of pi 1 of f on pi n of e comma f. But this map is an isomorphism because so this is an isomorphism. Because P is a vibration. But P lower star kills all elements of pi 1 of A. And so, if I take an element in pi 1 of f, apply it to some element of pi 1 of the relative pi n, the result would be the same as what I get by first projecting everything into pi n of b, and then applying the image of gamma there. But the image of gamma is trivial, so the action is trivial. Does this explanation explain anything? Okay, so this was the easy part. Now for the complicated part. So we want to prove the lemma, and we want to prove that if the action happens to be trivial. By the way, I've forgotten one important condition in the lemma, which is not relevant for proving one direction, but which is very much relevant for proving the other direction. The condition is the fiber k pi n plus 1. In one direction, we don't need this, but in the other direction, we very much do. So what do I mean when I say the fiber of a CW pair? Well, I mean the homotopy fiber of the inclusion map. Does this expression make any sense? I replace this map by a vibration, and this vibration has a fiber, and I want this fiber to be a k pi n, or n plus 1, since this is what we will need to apply it to. Well, by some group, yes. Okay. Well, as I said, there are several ways to generalize the theorem for non-abelian spaces. Я не понимаю вопрос. Значит, если x это kg1, то что? Значит, ну, для некоторых, сейчас какая диаграмма будет коммутативная? Значит, ну да, значит, значит, ну, значит, pullback расслоение путей. Значит, какого расслоения путей? Значит, ну значит, смотрите, если я беру пути от чего-то, пути h-пространства, у них, значит, P1 Абелева, правильно? Петли, да. Значит, у h-пространства, значит, P1 Абелева. Значит, поэтому вот, значит, допустим, мы хотим реализовать Kp1 как омега Kp2. Ну, для Абелевых это, значит, значит, так и работает, и все хорошо. Значит, для неабелевых, вообще говоря, вот это, значит, уже смысла никакого не имеет. Сейчас, значит, давайте, может быть, после этого, я по-прежнему не понимаю, значит, не понимаю вопрос, давайте мы обсудим после. Anyway, let's try to prove the other part of the lemma. So we have this inclusion A in X, and my claim is under these conditions, there is a way to extend this to extend the diagram. Okay, now. Since I have this condition on the fiber, which is Pn+1. Okay, since I have this condition on the fiber, the map. the map, the inclusion of A in X induces an isomorphism of the homotopy groups up to which dimension? Is it n plus 1, n minus 1, n plus 2? Which one is it? Well, let's try to remember the long exact sequence of the homotopy groups. The claim is if the fiber is k by something, then we have an isomorphism up to degree something. Now, what is this something? Does everyone agree? Yes? No? It's the fiber, not the base, that is k n plus 1. N plus 2. So there are three versions, n plus 1, n plus 2, and n. Which one is the correct one? If any. Well, so we have fiber, total space base, fiber minus 1. So, in particular, if we have in degree n, we have 0 because it's k by n plus 1. Total space base. So we will have isomorphisms in degree up to n, and what do we have in degree n plus 1? We have something non-zero, then pi n plus 1 of a, then pi n plus 1 of x, and then 0. So what does this imply about the map pi n plus 1 of a to pi n plus 1 of x? Yes, and as surjection. Of the pi n plus 1s. Okay, so using cellular approximation and more precisely some version of the cellular approximation theorem, we may assume that A contains the n skeleton of X. Does the word n skeleton make any sense? Now, there's a proof in Hatcher's book as usual, but before we move on, let's see an example. Let me take let me take, for example, X of dimension 2 and A, it's one skeleton. Then the map of pi zeros is a bijection, because the one skeleton contains something from every component, and the map of pi ones is a surjection. The pi 1 of A is free, and then when we add two cells, we add relations. So in this example, the claim seems to work. Basically, for hold on, is it the n skeleton or the n plus 1 skeleton? Let's think. So basically, A has enough cells to represent all elements of pi n plus 1, but not enough cells to kill all relations. So the claim is even better. A contains n plus 1 skeleton. If you disagree, please let everyone know. Okay. So now I want to use another black box. I want to use the Hurwitz theorem. No. It's probably CZ. Hurwitz theorem. We have two Hurwitz maps. We have the Hurwitz map for the pair x, A, and I have the similar Hurwitz, not sure if I'm pronouncing it correctly, map for the quotient space X by A. In general, none of these two arrows need be an isomorphism. But in our particular case, both are. And here is the only part of the argument where we need this condition on the action of by 1. Do we have chalk of any other color? We don't. Anyhow, so it is here that we use the action of by 1. And the second Horowitz theorem is straightforward. Suppose we have the n+1 skeleton of X included in the n+1 skeleton of A. Hold on, then something is wrong. We have 0 on the right, which doesn't sound correct. I've probably messed up the indices. It's probably n+1 is not very interesting. The n+1 skeleton of X is contained in A, so when we collapse A, there is no n+1 skeleton, and we get 0. So let me be more ambitious and write n+2 everywhere. And then what we get here is a meaningful statement. The first non-zero homotopy group is the same as the first non-zero homology group. Very well. So this part is clear. Well, this part is also clear. It's just excision. What about this part? Well, basically, the claim is that under these conditions, the Horowitz map is an isomorphism, the relative Horowitz map. Okay, I don't want to erase the lemma. We're almost done, so let's finish the proof and then have a break. Okay. Okay, so the n+1 skeleton of this space is 0. the the first the first non-zero homotopy group is by y. Let's look at these isomorphisms. My claim is, but my claim may be wrong. The first non-zero. My claim is basically the first non-zero homology group or the first non-zero homotopy group, which are the same of this space, is pi, and it lives in degree n plus 1. Sorry, n plus 2. Okay, so why is this true? It's a non-trivial fact. Let me remind everyone of this fact. So basically, there is a way to interpret the relative homotopy groups as absolute homotopy groups. The relative homotopy groups of any CW pair are the same as the absolute homotopy groups of the fiber of the inclusion map. Well, we know the fiber of the inclusion map. It's k pi n plus 1. So it has only one homotopy group in degree n plus 1. So the relative homotopy groups by I x comma a are I for I equal n plus 2 and 0 otherwise. Does this make sense? Again, please check the plus ones and minus ones. They might be wrong. Okay, so unless I've mixed up everything, we have this the group is equal pi. So the n plus second homotopy group of this space is equal pi, and then I kill everything else. I get a k by n plus 2, and this gives me this map. Okay, now. let me just turn it into vibration. I get an E here, which is basically the same space as X. Well, every vibration has a fiber. Let me call this fiber F. And well, let's look at this diagram. The map the composition A to X by A is constant. So for A, when we take this composition, ends up in a point, which means it ends up when we take this composition, it ends up in a fiber of F, in the fiber of this vibration. So this map exists for general reasons. Is it an isomorphism? Is it a homotype equivalence? Well, my claim it is. Why is it a homotype equivalence? Use the long exact sequence of the homotype groups. We have in the long exact sequence of the homotopy groups, in both cases, we have just one non-zero relative homotopy group. So we have pi n plus 2 x comma a, which maps to pi n plus 2 e comma f. But this map is basically given here. And it's an isomorphism. Why is it an isomorphism? Basically, because we pi n plus 2 x comma a, then we apply the Horowitz map, then then we end up by in x by a, and then we have another isomorphism by n plus 2 of x by a, 2 by n plus 2 of the base space, k by n plus 2. And all those maps are isomorphisms. Okay, I've run over time. Sorry about that. Does the proof make any sense? The answer is no. Okay, how bad is it? Okay. Okay. Well, my suggestion is let's have a break, and after the break, let's discuss any parts of the proof which don't make sense. let's continue. Basically, before the break, we proved this lemma, and as we as we noticed during the proof, there is just one relative homotopy group, so the condition here is really about this group. There aren't any other groups. Okay, now let's look at the proof again and see which parts make sense, which parts don't. I'll close the door. Hopefully, although looks like there aren't any. There aren't any people at the moment, but who knows? Maybe they'll appear out of nowhere at some point. Anyway, dilemma. Does the proof make some sense, no sense, or perfect sense? The last part. Well, we have constructed the diagram basically by saying A to X by A, which is a cofibration sequence, and then we map the cofibration sequence into a fibration sequence, and the map here is obtained by killing off the higher homotopy groups of X by A, which may well be non-zero, but we kill them off as usual, and the result is an Eilenberg-MacLane space. Very well. Now we have the composite arrow, which we may turn into fibration. We call this fibration E, and for general reasons, basically said theoretically, we have this map. So we have a map of pairs, X comma A to E comma F. We want to prove on the level of X and E, we have a homotopy equivalence, and if we do the same for the relative homotopy groups, then we have a homotopy equivalence for A to F. Now we want to. There is just one non-zero relative homotopy group in both cases. It's the n plus 2 pi n plus 2. We want to study the map of these, and well, by construction, both are isomorphic to pi, and the map here commutes with some isomorphisms to pi. Why? Well, let's recall what this map does. We first identify these two groups which in general have nothing to do with each other. The relative pi and the pi of the quotient. For homology, these are the same. For homotopy groups, may or may not, it depends. But in this case, the natural map from here to here is an isomorphism. We're in log. And on the other hand, the pi n plus 2 of the quotient is basically by construction the pi n plus 2 of the base. So by construction, the map here is an isomorphism, and so we have a homotopy equivalence here as well, and we've proved the lemma. Any more questions? Okay. Now, I'm sorry, what's your name? Andrei. Andrei, during the break, has mentioned one thing which is quite interesting. In the proposition, we do not need to assume that the action of pi 1 on all homotopy groups is trivial. Only on the zeroth one, only on the second and higher homotopy groups. Let's see if this works. So we want to prove the proposition. Okay, I'll start here. Proof of the proposition. Well, let's remind ourselves of what the proposition says. N+1 xn plus 1 xn, our principal. Meaning that there is an extension such that both pieces of the sequence are vibration sequences, if and only if the action of pi 1 on the higher homotopy groups is trivial, and we do not need to assume that the action of pi 1 on itself is trivial, which is the same as pi 1 abelian. Okay, let me keep the lemma. We will basically use this lemma to prove the proposition. Well, this is what Andre says. Let's see whether or not he's right. I have two actions. So pi 1 of x, on the one hand, it acts on pi n of x, and on the other hand, pi 1 of okay, so in our case, x will be xn, a will be xn plus 1. So pi 1 xn plus 1 acts on the homotopy group pi okay, let me put an I here. Pi I x n mod x n plus 1, which is which is something I can define if I turn the map xn plus 1 to xn into a cofibration. In other words, into the inclusion of a CW subcomplex. And I want to see what these two actions have in common. Maybe nothing. Let's see. And moreover, the only group I'm interested here is pi n plus 2. Well, first, the first remark, pi 1 of x plus 1 is the same as pi 1 of x. No surprises there. Is there a way to identify these two groups? Well, let's see. Pi n plus 2 of xn is 0. Xn has no homotopy group starting from the n plus first one. Then I have the relative homotopy group xn x n plus 1. Then I have the pi n plus 1 of xn plus 1, which is not necessarily 0, but then I have pi n plus 1 of xn, which is 0. So the map in the middle is an isomorphism. And moreover, it's an isomorphism of pi x n plus of pi 1 xn plus 1 modules, which is again general nonsense. So I'm able to identify this action with what? This action, which I want to be trivial, is isomorphic to the action of pi 1 of xn plus 1 on pi n plus 1 of xn. And I want this action to be isomorphic to the action of pi 1 of x on pi n plus 1 of x, which is also clearly true. So this action is isomorphic to this action, and then let's see where the Bosnikov tower starts. It starts normally at n equal 1. So we want this map to be a principal fibration only for n equal 1 and higher, because at the moment we don't have an x naught. We only have x1. Okay, so we need this action to be trivial for n greater than or equal 1. So indeed, what we need to be trivial is the action on pi 2 and higher homotopy groups, not necessarily on pi 1. Are there any questions? Okay, so we have proved the proposition, I think. Am I right? I may be wrong. Имеет ли происходящее хотя бы какой-нибудь смысл? Good. Okay. Now, are there any questions? Okay, now let's again briefly review some obstruction theory. We will only cover the parts of it which we will need for localization. There's more to obstruction theory than we'll talk about today. Okay, so given this diagram with X connected abelian, is there a dotted arrow which makes the diagram homotypic commutative? And if there is such an arrow, how many are there? Maybe there are two arrows, and those are not homotopic, or three. Okay, so we will define an obstruction homology class, and the class vanishes if and only if an extension exists. And then we'll define another homology class, and this other homology class vanishes if and only if the extension is unique. And this is basically typical things one can expect to get out of obstruction theory. There are two ways to do obstruction theory. Way one is to consider scalar of W, and way two is to consider the stages of the Postnikov tower of X. We'll follow the second route. Since we assume X abelian, extend the Postnikov tower a little bit. So I have x1 goes to k by 2, 3, and so on. But I also can attend an x node at the bottom, which is just a point, and basically this composition is a principal vibration. What does this mean? Well, this means that x is a k by 1, k by 1, 1. And observe that here we do need the space to be abelian, because otherwise the space in the bottom right corner doesn't make sense. Anyhow, the idea is to construct the extension stage by stage. We have an x. We already have a map from A to X, so we can compose this map with any of the arrows in the Postnikov tower. Very well. So in particular, we have this map from X to any stage of the Postnikov tower. Suppose we somehow manage to construct a map from W to Xn, and we want to extend it. Well, the vibration is principal. Let's just assume that all xn plus 1 to xn are principal vibrations. Where P means the path space of all paths which start at the base point. Okay, now by construction, xn plus 1 is the set of all x comma gamma in xn cross b. Let me write this thing as just b, such that kn of x is gamma of 0. No, gamma of 1. So the map from the path space to the k something takes every path to its endpoint. The starting point is the same for all paths, and the endpoint varies. Now, my claim is to construct a lift from W to xn plus 1 is the same as to construct a homotopy from the composite map W xn k xn plus pi n plus 1 n plus 2 now the constant map. Let's see why. Well, if I have a lift, then for every element of xn plus 1, for every element of W, I have a point which connects I have a path gamma which connects the image of the element of the element of W here with the base point. Does this make sense? Suppose I have some element of W. Suppose I somehow managed to construct x comma gamma. What does gamma do? Well, gamma connects k1 of x, where x is the image of W in xn. With the base point, well, basically because B is the space of all paths starting at the base point. Does this make sense? Okay. Moreover, on A we have we already have a map from A to X, meaning we have this map, and we already have a homotopy between the composite A goes to xn plus 1, goes to k n plus 1 and plus 2, and the constant map. Well, the homotopy is I'm thinking whether or not the map when restricted to A is already constant. Well, I don't see why it should be on the nose, but since we know the extension exists, it's at least homotopic to a constant map. In other words, we have okay. So on A we have a homotopy. In other words, we have the following diagram. Since we have a map from W to the k pi n plus 2, no, n plus 1 and plus 2. And since we have a homotopy of the restriction of the map to A, we can extend the map to the cone. And the question is, when does this map extend to the cone over W? And the answer is the extension exists if and only if the map itself, this map itself, is homotopic to the identity, to the constant map, or in other words, null homotopic. And this is equivalent to omega n, where, sorry, let me call this omega n plus 1. Inside h n plus 2 k, no, w union c a by n plus 1, which is the same as hn plus 2 w a by n plus 1 is 0. And this omega is the class which corresponds to this map. And so we have defined the n plus first obstruction. let me state the proposition. The yes, if and only if all omega n are 0 for n greater than or equal 0. Where omega n is the class we've just defined. Does this make sense? Are there any questions? Now, there's one thing we need to say. One more thing we need to say in order to prove the proposition. What's the relationship between the Bosnikov tower and the space itself? Is there any relationship? So basically, even if we have extended, we have the extensions from W to xn for all n. What's the benefit? Let's see. Well, first of all, starting from the Bosnikov tower, we can construct the inverse limit. What's the inverse limit? It's just the inverse limit in the stupid sense. We take the spaces x1, x2, and the rest. We take the product with the product topology, and we basically take all elements which all sequences such that every element is the image of the next element. The limit in the inverse limit in the naive sense. In particular, this space need not be a CW complex. May not have a CW structure. But there's at least a map from there is a map from X to the inverse limit, and this map is a weak homotype equivalence. So the homotopy groups of the homotopy groups of X are the same as the homotopy groups of the inverse limit. And then we if AW is a CW pair, we have okay. I'll erase this part. So I have I decompose the map as an inclusion followed by strong homotopy equivalence, and in particular, I get I get a diagram, like the one I've shown on the board, and by general topology, essentially, there's a way to using the fact that W is a CW complex. There is a way to homotope the map from W to the cylinder back to X, whilst keeping it fixed on A. In other words, we need a little bit to complete the argument to make sure the map from W goes to X and not the inverse limit, but it's feasible. Okay. Any more questions? Any more questions? Цилиндр, значит, он появился из тех соображений, что значит, у нас отображения, которые мы построили, они оказываются здесь. Но мы хотим отображение сюда. Ну, как нам сделать так, чтобы значит, и вот это значит, жили бы где-нибудь в одном и том же месте? Ну, нужно взять цилиндр. Okay. Well, we have. Is there anything else I want to say with regard to this proof? Oh yes, one more thing. when I'll just say one more thing, and then we'll decide whether or not we want to go any further. We still need to be able to say when any two extensions are homotopic. So we have this extension from W to X when is the homotopy class unique? Well, assuming all obstructions vanish. Let me state a sufficient condition, and this is all we will need for localizing spaces. Sufficient condition. Well, Hn plus 2 of W cross 0, 1 model A cross 0, 1 cop W cross 0, 1 with coefficients in pi n plus 1 equals 0 for all n greater than or equal 0. Okay. Is it clear where the statement comes from? The proof is exactly the same, but this time we what do we have? Let's draw a picture. Let's imagine ourselves a reel. So we again proceed by lifting a homotopy between two extensions from xn plus 1, no, from xn to xn plus 1. So this is at each stage we have our two extensions which are defined on both the top and the bottom of the real, and we have the constant homotopy on A cross 0, 1. And we want to extend this to a homotopy. So this real is empty, meaning there is no cable on it, and we want to extend the map to the real with the cable, and which is W cross 0, 1. When is it possible? And we proceed in exactly the same way. This is possible if and only if the map from W cross 0, 1 union the cone on the real to k pi something extends. Well, this is the same as to say that the relative homology. This will definitely follow if the relative homology is 0. This is the group where the obstruction lives in. In our case, the group will be 0 when because by n plus 1 in our case will be 0. The coefficient group will be 0. Okay, does this make sense? Значит, понятно ли, что происходит? Значит, происходит то же самое, что раньше происходило, только мы хотим. Ну, вот раньше у нас там было А и W, и мы хотели что-то распространить. Сейчас вместо А и W там мы хотим, то есть раньше мы хотели распространить это выражение, а сейчас гомотопия. Но больше ничего не происходит. All right. Are there any more questions? We basically. My suggestion is to call it a day and start the proof of the theorem next time. What do you think? Хотим ли мы сейчас начинать доказательство теоремы, или мы не хотим и начнем его в следующий раз? Окей. Ну, там по умолчанию я думаю, что I think it would make sense to postpone the proof of the theorem because everyone's tired. This doesn't include the lecture. The lecture is the lecture doesn't matter, but everyone in the audience is tired. But basically, while one is lecturing, there's less chance one would fall asleep. It still happens, but it's rare. Anyway. Okay. So, are there any questions on what we've just done? Well, let's call it a day. in this case, and then we'll prove the localization theorem next time.